Hello students, in this video we'll find the Ricci and scalar curvature of the upper half space with the hyperbolic metric. Let's consider h, which is the set of all points x and y, such that y is greater than 0, equipped with a metric, hyperbolic metric, which is ds squared, is dx squared plus dy squared over y. This is hyperbolic space, this is the hyperbolic metric. It's one model. Okay? And so we want to do the Christoffel symbol so that we can compute the Ricci tensor and so we can compute the Riemann scalar curvature. So let's do so. So let's compute gamma of 1, 1, 1. That's d by dx of what? It's d by dx of the log of the 1, 1 component, the log, the square root of the 1, 1 component, which is the square root of y to the negative 2, right? And then, of course, it's just going to be 0. What is gamma of 1, 1, 2? Like this. Let's figure it out. So that's going to be the y derivative of the same thing. So it's going to be the y derivative of the log of the square root of y to the negative 2. And, of course, that's just y to the negative 1, so that's just going to be a negative 1 over y. And then what is gamma of 1, 2, 2 going to be? Gamma of 1, 2, 2 is going to be negative 1 over 2 y to the negative 2, then an x derivative of what? Then an x derivative of y to the negative 2, y to the negative 2, which is 0. So those are the Christoffel symbols where 1 is the upper index. Let's look at the Christoffel symbols when we have a 2 as the upper index. If you look at gamma of 2, 1, 1, what will that be? Well, that's going to be negative 1 over 2, y to the negative 2, and then d by dy of y to the negative 2, right? And so that's going to give me a positive, because the 2 is going to cancel, the negative is going to cancel out, and I'm going to have a 1 over y positive. That's the only one that's going to be positive of the Christoffel symbols. Okay. And we look at gamma 2, 1, 2. What are we going to see over there? Well, that's just going to be the what? That's just going to be the x derivative of the log of the square root of y to the negative 2, and that's just 0. And let's finally do gamma of 2, 2, 2. That's the y derivative of the log of the square root of y to the negative 1/2 to the 1/2 power, right? And of course, that's just going to give me a negative 1 over y. So we have all of our Christoffel symbols. Let's just highlight the ones that aren't 0, because that's going to be essential when we do our Ricci tensor, right? So this guy over here, not 0. This expression over here, not 0. And then this expression over here, not 0. Those are the only components of the Ricci tensor which are not, the Christoffel symbols which are not 0. Great. All right. So now let's recall what the Ricci tensor is. So our Ricci tensor, Rij, is what? Is d by dxl, gamma Lij, and then minus partial squared, partial xi, partial xj, and then we'll have a what? Then we'll have a log of the square root of g, the determinant of the metric tensor, and then a plus, then we'll do a gamma ij l d by dx l of the log of the metric tensor, then minus gamma I a gamma j l l a, like that. That's our Ricci tensor. Ricci tensor. Okay, excellent. And so now what I want to do is I want to compute these things, so let's do them slowly, right? So let's look at R11, for example. So R11. Now that means I'm going to plug in I and j are 1 and 1. Now the only time we have a 1, 1 entry that exists is this upper index of 2. So L is going to have to be 2 in this instance, right? So when L is equal to 2, we're going to have a d by dy, and then a gamma 2, 1, 1. And then over here, what are we going to have? We're going to have an x derivative and x derivative, because I have a partial x1, those corresponds to x. So those terms are going to be gone because I have x derivatives and there's only y's in the Christoffel symbol. So those terms are gone. Then these terms over here are going to have to correspond to a 1, 1. So I have gamma is equal to L. When L is equal to what? When L is equal to 2 over here, so we'll have a what? When L is equal to 2, we'll have a plus gamma and then 2, 1, 1. And then the y derivative of the log, and the determinant of this is going to be y to the negative 4 power, so that's going to be a y to the negative 2 over here, y to the negative 2. And then we're going to have what? Then we have these, so we've taken care of these terms over here. Now we have all these mixed terms to deal with, right? So that's going to be a what? Minus gamma 1, 1, 1, 1, 1, 1. That's one possibility. Plus gamma 1, 1. I could do a 1, 1, 2, 1. plus gamma 1, gamma 1. I can do a 2, 2, 1, 1. I can do a gamma 1, gamma 1, the 1 goes upstairs, so that's not 1 up there. You have to be real patient with these calculations. Gamma, gamma 1, and then a 2, 2, 2, 2, like that. Great. Now let's slowly do these things over here. So this is the y derivative of what? This is the y derivative of gamma 2. So it's going to be a negative 1 over y squared. Then I'm going to have a what? So over here I'm going to have a plus gamma 1, 2, that's a plus 1 over y. And then this derivative of the log of y negative 2 is going to be a negative 2 over y. Great. And then minus what? Gamma 1, 1, 1 is 0. So that term is gone. That's gone. Gamma 1, 1, 1 is also 0, so that's gone. And that should be actually a 2 up there, my summing. So let's make sure we got that correct. So I have a 2, 1, 1, so that's not 0, and a 1, 1, 2, so that's not 0. So this term is not 0. Let's make sure we got the right index summation over here. So what will that term be? That's going to be a 1, 1, 2, which is negative 1 over y, and then that term over there is going to be a 1 over y, so it's going to be a negative 1 over y squared for that term over there. This term right here is negative 1 over y, not 0. And then this term over here is exactly the same thing, so it's going to be another negative 1 over y squared. And then gamma 1, 2, 1 is going to be, that term is going to be 0 because there's no gamma 2, 1, 1, right? So all total, what do we have? All total in these parentheses over here, I have negative 2 over y squared. I have a negative 2 over y squared over here, but this negative turns those into a positive, so those are going to cancel out, and we're going to get negative 1 over y squared. Excellent. That's in the first component of the Ricci tensor. The next component, see what we get. So let's do a r of 1, 2. Now I have a 1, 2 as my index over here, right? So my index ij is 1, 2 for these Christoffel symbols. And the only time that I have a 1, 2 is when the upper index is a 1, right? So what I have is I have an x derivative. So this term over here will give me only an x derivative because I'll have a partial x1, gamma 1, 1, 2. And so that won't even be there because there's no x derivative. I have a 1, 2, I have one x derivative over here, so there's no derivatives over there in this term because there's an x derivative of only y, so those first two terms are completely gone because over here I have a gamma 1, 2, and then a 1, that's the only non-zero one. And then that will cancel, and let's look over here. So again, I'm going to need a what? I'm going to need gamma to be equal to 1 over here, right? So what will happen is if I have gamma equals 1, I'll have a partial with respect to x, and so that will be 0, again gone. Let's start with these last couple terms. So I have a 0 plus 0 plus 0, and then minus, I'll have a gamma 1, a gamma 2. I could do a 1, 1, 1, 1, like that. I could do a gamma 1, gamma 2. I could do a 1, 2, 1, 2, like that. I could do a gamma 1, gamma 2. Now I got to do a 2, 2, 1, 1, or I could do a gamma 1, gamma 2. I could do a 2, 2, 2, 2. Okay, great. Now let's see what's going to happen over here. So gamma 1, 1, 1, 1 is 0. Gamma 2, 1, 1, 1 is a 1 over y. And then the gamma 1, 2, 2 is a 0. Then the gamma 1, 1, 2 is something, but the gamma 2, 2, 1 is going to be 0 because by symmetry. And finally, the gamma 2, 1, 1 is going to be equal to 0. So all these terms vanish. So the Ricci tensor is 0 at the Ricci tensor component 1, 2 is 0. And that's the same thing by symmetry is R 2, 1. Great. Okay. Let's do the last calculation. So what will the last calculation be? It's going to be R 2, 2. And so that corresponds to I and j being equal to 2, right? So the only time I have a 2, 2 in the fractions when L is equal to 2, right? So it's going to be a d by dy of what? Of gamma 2, 2, 2. This is two y derivatives now, so minus partial squared, partial y squared of the log of y to the negative 2. And then we have these terms over here, so I have 2, 2, so I need L to be 2, so it's going to be gamma of 2, 2, 2. Partial y of the log of what? The log of y to the negative 2. That's what the square root of b is. Yeah. Then minus all these terms over here. I can have a gamma 2, a gamma 2. I could do a 1, 1, 1, 1. I could do a gamma 2, a gamma 2, a 1, 1, 2, 2. I could do a gamma 2, gamma 2. And I could put a 2, 2, 1, 1. Or I could do a gamma 2, a gamma 2, a 2, a 2, a 2, a 2, like that. Okay, so there's all the terms we have. Let's gather them and do them slowly, right? So what's the y derivative of the 2q component? That's going to be a negative. So now it's going to be a positive 1 over y squared, like that. That term was negative, right? So we didn't really get positive. Now let's think about this carefully. So I can pull that negative 2 over here. Let's plug out that, turn that negative 2 into a positive 2. Then I have the first derivative, which is going to be 1 over y. And the second derivative is going to be a negative 1 over y squared. So it's going to be a negative 1 over y squared. So that's negative 1 over y squared. Negative 1 over y squared. Good. Then I have a negative 1 over y, and then this is going to be a what? This is going to be a, pull that negative 2 out of everything, so I have a negative 2. Then that's going to be a negative 1 over y over there, and then a 1 over y. Okay, great. And now let's count these terms over here. So we're going to have total over here. So total over here, we're going to have a what? A gamma 1, 2, 1. The gamma 1, 2, 1 is going to be equal to negative 1 over y, negative 1 over y, because of bisymmetry. So that's going to be a negative 1 over, so that's a positive 1 over y squared. This term over here, gamma 2, 1, 2 is going to be 0. Gamma 1, 2, 2 is going to be 0. Good. And then gamma of 2, 2, 2 times 2, 2, 2 is going to be a negative, so a positive 1 over y squared. Positive 1 over y squared for that one. Great. And let's count what's going to happen over here. So I'll have this positive 1 over y squared, right? So these terms and these terms are going to cancel out. And then I have 2 of these and 1 of these over here, so that's just going to be negative 1 over y squared. Beautiful. So now what we've done is we've shown the following. We've shown that our Ricci tensor, Rij, is really negative 1 over y squared, 0, 0, negative 1 over y squared, which is equal to the negative of the metric tensor. Beautiful, right? And so now what that tells me, it tells me 2 things. It first tells me that this space is an Einstein space. It's an Einstein space. Beautiful. And it also gives me, when I trace the Ricci tensor now, I can automatically conclude that R, the scalar curvature, is going to be what? It's going to be Gij upper, Rij lower. And now since these matrices are exactly the reciprocals of each other, the self-inversions, I'm going to get that when I do the inverse of this thing over here, of the metric tensor. So our metric tensor, if we look over here, is just going to be this thing over here. So the inverse of that is going to be positive, is going to be y squared, 0, 0, y squared. When I hit that with the Ricci tensor, I'm going to get a negative 1 plus negative 1. So the scalar curvature of this space is negative 2. So this is a space of constant scalar curvature. And in the constant scalar curvature case is one of the most elementary cases we can think about for scalar curvature, right? It's not varying, it's always equal to negative 2. We saw in another video that the scalar curvature of the unit sphere was also equal to 2, right? And so we have this example of a positive scalar curvature, a positive constant scalar curvature manifold being the unit sphere. And now we have the upper half space with this hyperbolic metric being a constant scalar curvature manifold with constant scalar curvature negative 2. So I have a positive scalar curvature for the sphere and a negative scalar curvature for this hyperbolic space. And we can show this hyperbolic that the upper half space is isometric to one of these Lobachevsky pseudospheres, which is sort of another classical model of hyperbolic geometry. So there's different isometric versions of this upper half space. Namely, there's a disk model for hyperbolic geometry, and then there's a hyperboloid sheet model for hyperbolic geometry. The coefficient calculations in the upper half space tend to be the easiest calculations you can do. And this gives a great example of a calculation where you can actually compute the scalar curvature explicitly, the Christoffel symbols explicitly, and prove that you have an Einstein space for this hyperbolic space. Thank you very much.